All right, I'll talk about statistics and big data at Google. Let's start by looking at some data. So at Google, we look at big, serious, important questions. When are the most searches for hangover? Okay, there's a little peak there. Imagine that. Interest over time, okay? So pretty steady, and then all of a sudden, around 2009, there was a big spike. What happened? People drank more? No, a TV show or something. Where do people search for hangover? So these are some of the things you can go look for on Google. Yeah, not too bad here. Related terms, cure for hangover, hangover cures, hangover food, etc. Love hangover? I don't get that. Hangover and vodka. There's some correlation there. This is an interesting one. Who searches? Boyfriend or girlfriend? Searches for boyfriend, searches for girlfriend. And then compare that to the next one. Okay, so we notice that the girls do more searches for their boyfriends. Husband and wife. All right. Searches correlated with weight loss. Losing weight, best vacation spots, low calorie. Searches correlated with weight loss. Okay, so here's weight loss and vacation spots. Big spike around New Year's. Weight loss 3 weeks later. Not losing weight. Weight loss plateau. Used car dealerships. All right, so switching gears a little bit, let me tell you about a project that I did related to that. So we're looking at billions of queries. So the correlations that we were looking at, how does that work? It's not done by, you go to Google, you do a search, and then once you've done the search, then we go process the data and give you the answer. Because that's going to take a long time, right? What we want to do is figure out the most popular things that people care about so we can pre-compute results and cache them. So I did a project related to that. We're looking at billions of queries, trying to predict the general pattern over the course of the day, course of the week, so that we know what are the popular queries so we can cache the popular queries and give results quickly. And so we can look at spikes and dips for something interesting going on. Like in the bottom here, we've got queries for Facebook. And in red is the actual data, and in blue is the fit. And we see there's a pretty regular pattern, and all of a sudden there's a spike, which happened because there was an outage. Incidentally, yes, people do come to Google to search for Facebook. We call that a navigational query. So in this project, we want to process billions of queries, predict the regular pattern, and look for spikes and dips. So some of the applications of this, including the caching, the Google Hot Trends, breaking news, trending videos, etc. So we have to handle billions of queries. We want to do it in low memory because even though Google has terrific data systems, we're still talking about a lot of queries, billions of queries. So we want to do it in low memory. It has to be distributed. Everything at Google is split across tens of thousands of machines. There's nothing that fits on one machine. Has to be accurate, include time of day and time of week effects, reasonably accurate. We don't need huge accuracy for this. And we have to work with different time scales. Here are 3 different patterns that you may see. The top one is for Yahoo. Yes, people come to Google to search for Yahoo. So we see a pretty regular pattern of the course of the day, and then it's lower on the weekends. Then the next one is bachelorette. There's one time of the week when there's a big spike for that, okay? Just before the show comes on and during the show. TV guide at the bottom. Okay, so different patterns for different queries. This is a little picture of how things work at Google. The data is stored on these tens of thousands of machines. And that affects the kind of processing that we can do. Processing where we basically take sums. How many of this occurred? That's pretty easy because we can count on all the different machines and then combine the results. Things that don't work so well are things like the median, where normally with small data you sort the data. And sorting the data when it resides in all these machines doesn't work so well. So the data is residing on all those servers. That's our raw logs data. We process it. We collect the data. We reduce it. And then finally, we get the result either to the statistician or to serve. Okay. Any questions? All right. The particular thing I did involved Poisson regression using a spline basis. How many of you do statistics? Good, I would expect. How many of you are familiar with splines? Okay, quite a few. Basically, the idea of splines is there's some relationship between y and x. And one way that you might model that is with a polynomial. Y equals a plus bx plus cx squared, et cetera, et cetera. That tends not to work so well for a lot of the data that we deal with. Splines work better. These polynomials kind of blow up at the ends, and they don't work so well for something that's periodic. The splines is something that is sort of more localized. And so the particular thing that I did involved estimating data initially, and then as time goes on, instead of going, when we get new data, instead of starting over and re-estimating all the coefficients, starting from scratch, that would be very expensive. We don't do that. Instead, we just update the estimates. It's an approximation. It's not exact, but it's pretty close. Okay? And we do it in pretty low memory. We've got 24 coefficients for the time of day, and then 7 coefficients for the days of the week. So for billions of queries, we've got 30 coefficients each that we update. So this is one of the applications, the hot trends. And before we go further, no, skip that. OK. So now we'll move on to talking about experiments at Google. How Google makes money. You do a search, we show you ads, right? Yeah, or maybe not. This is the kind of searches I do. I don't see a lot of ads. But when I was searching for a new car, when somebody ran into us, totaled our car, all of a sudden there were a lot more ads, and I was actually interested in those ads. That's kind of the ideal for Google. We don't want to show ads if you don't want to see ads. We want to show ads when you're interested in the ads. If we show ads when you don't want to see them, you just get turned off. We call that ad blindness. Okay? So one of the things that Google is trying to figure out when people want to see ads. So back to this, when somebody's searching for flights to Hawaii, they may be interested in an ad. So we'll try and show that. So this is how Google makes money, ads and things like this. And we put a lot of effort into the search page, imagine than that. A lot of effort into the search results, and a lot of effort into when are ads appropriate and then what ads are best. And we do lots of experiments. Google, people may have what they think is a great idea. We test it. So we're doing hundreds of experiments, thousands of experiments every year, hundreds of experiments at any given time. When you come and do a search in Google, you're probably in the active arm of a dozen experiments. Things to look at: different tweaks to the search results. Maybe we have a new signal that we think would help improve the search results. We'll test it. We'll send 1% of the traffic to serve using this new algorithm. You'll get slightly different search results. And then we look at, did that actually seem to improve your happiness? Now, how do we judge that? Well, if we give the top search result and you click on that, that is an indication that you like that. If you go to that page and then pretty quickly come back to look for something else, that's an indication that that top page wasn't so good. So we use indirect signals like that. So we're doing all these experiments. We're looking for small effects. Okay? 1/10 of 1% improvement. Okay? It's hard to detect things like that, right? But when you're talking about data the size of Google, the number of people coming, an improvement like that matters because it's affecting a lot of people. Plus, we're making lots of these improvements, as many of these as we can, and over time we get better. So there's lots of different types of experiments we do: one-shot experiments over the course of the day, geographic, et cetera. Guy that sits with me in my office, Statistician, was instrumental in setting up this infrastructure at Google for running the experiments, and is still quite involved with it. And I kind of know how things are going, but how much swearing I hear from behind me? Do you guys remember when Google Instant came out? So Google Instant, remember when you used to have to type your query and then hit return? Okay, Google Instant was, we're going to start giving you results as you're typing. There was a lot of swearing. Because that was changing pretty much everything. Used to be that our unit of observation was the completed query. Now it's every character that you type and when you backspace. Okay, and as soon as you, and if we're showing results and you don't click on that immediately, well, that's a negative signal. So it very much changed all of the statistics that we had to do. Let me talk a little about running your own experiments. Google Web Optimizer, and this actually got me to Google. I'll tell you about that in a bit. So Google Web Optimizer, the idea is you've got a website and you want somebody to do something. Buy something, download some software, make a donation. And you've got, and you want to make your website as effective as you can. Well, what you can do is create multiple versions of your website, of your page. There's the default one. You add some JavaScript from Google to that page that when somebody comes to that page, randomly leaves them there or sends them to one of the other versions. And then you want somebody to do something like maybe click a particular button, follow a particular link. So you add some JavaScript that records that. And then people come to your page. The Google JavaScript sends them to one of the arms and records what they do, and then gives you the results. Okay. And it was called Google Web Optimizer. Now it's part of Google Analytics. So you send 1/3 of the visitors to each page. They're a little bit different, and you see what happens. And at Google, we do what's called dog fooding, eat our own dog food. We try things out ourselves. So Picasa, the image software, the photo software, tried this out. Can we improve the number of people who download Picasa? So this was one page, and the circled in red are the 4 elements of this page that we're going to try and modify. You could do just what we call a simple A/B test. I've got 2 versions of my web page. In this case, we've got 4 factors that we want to try. Okay? What text do we use in the top left box? Do we include a screenshot at the bottom? What kind of screenshot? Okay? So it's a 4-factor experiment. And here are 2 versions of the page. Which do you think would be more effective? Who thinks the left? Who thinks the right? Okay, so we ran an experiment. Whoa. The second page increased the downloads by 30%. So it's got instead of free download, it's got Try Picasa Now. That's a little more action-oriented, a little more bold. I guess that worked better. The screenshot turned people away. Maybe just having the screenshot, they found something they didn't like about it. It was too complicated. Who knows? So we just tested. Okay? Any questions? Any comments? Yeah. Say again? I don't know exactly what you mean by that, but. I don't know. It might have been that you were in an experiment. Okay. Maybe that experiment was. We're running all these experiments, so different people are not always going to get the same results. We're tweaking things. We're trying things out. No, just you. Only you. Yeah, I don't think so. Maybe there are some experiments that are doing that, but not that I know of. Okay. So some issues with this. Well, we're doing multiple testing, and multiple testing is problematic. If I have, say, 16 versions of my page, my default, and 15 others, and I test ARM2 against the default. Is ARM2 better? I'll run a statistical test with a 5% false positive rate. And then I do the same thing with ARM3 and with ARM4 and ARM5. By the time I run 15 tests against ARM1, even if none of them are really better, I'm probably going to claim that one of these is better with statistical significance. We're also dealing with with looking at data over time. People are, we're providing the results to people immediately online. And if they look over time and say, look at the data 10 times, is ARM2 better than ARM1 with 5% significance rate? By the time you do it 10 times, you've got a pretty good chance that you're going to claim something significant even when there's not. So I had some background with this that I'll come to in just a bit. So little background on experiments. The experimental infrastructure in statistics, a lot of it was set up for agricultural experiments. Some of you know something about this. Set up by Sir Ronald Fisher back at Rothamsted. And there, you basically have to set up the experiment at the beginning of the growing season. You determine which plots are going to get which seeds, which fertilizers, irrigation if you're doing irrigation, et cetera. And then you collect the data when you harvest the corn. So you plan in advance and you analyze at the end. In clinical trials, you take multiple looks at the data, but not continuously. And on the web, we go one step further. We can analyze the data pretty much continuously. Every time we get a new observation, we can reanalyze the data. So this is an example from clinical trials. This is the background that I had, where at the S+ company, I had worked on S+ Seq trial, Sequential Designs for Clinical Trials, working with Scott Emerson at the University of Washington. The magenta line over there represents what would happen if you do a fixed sample trial. We plan in advance that we will enroll 6,000 subjects over a period of 2 years. And at that 2-year mark, we will analyze the data. And if the difference in survival probabilities falls above that little mark over at the right, then we have statistical significance, a positive result. And if it falls below, we don't. But we don't want to wait 2 years. We want to look at the data as it's coming in, and if this new treatment looks like it's really good, then we want to get it out there and saving lives. If it looks like it's really bad, we want to stop early and quit killing people, right? So with the sequential design, what we do is we plan that we will look at the data after 1,900 observations, 3,800, et cetera. We'll take 4 looks at the data. And at the first look, if the difference in survival probabilities is really good, if we hit that, can you see that? If we hit this mark or higher, then we're going to stop and declare a positive result. If we hit this mark or lower, then we stop and declare a negative result. And if we're somewhere in between, results are ambiguous, then we'll continue on to the next trial. These diagonal lines are just for show. They don't actually have any effect. We continue on to the second trial. Do we fall above the upper boundary? We stop. Do we fall below the lower boundary? We stop. Otherwise, we continue on. You with me on that? Okay. So doing this, we design it so it has the same power as the classical trial. And because sometimes we stop early, and stopping early, maybe we make a mistake, we don't have as much data. As a result, we have to have the final look be more subjects than if we did the fixed sample trial. We may run out to 7,500 subjects there. So this could end up being more expensive than the fixed sample trial. But on average, it's cheaper. The top magenta line is how many subjects you use with the fixed sample trial. It's always 6,000. And the cyan curve indicates what would happen on average, how quickly would you stop on average, depending on the true difference in survival probabilities. So suppose you've got a really good treatment, then what's going to tend to happen is you're going to tend to hit one of those early upper boundaries and stop quickly. If you're really bad, you're going to tend to hit one of the lower boundaries and stop quickly. So in either of those cases, you're going to tend to stop fairly early. Even if you're kind of in the middle range, you'll tend to stop earlier than with the fixed sample trial. Okay? So on average, you save money. On average, you get this thing out quicker. One of the, I believe the first trial that actually stopped early was for the drug AZT for treating HIV. Okay? Back when, in the early days of HIV, there was no treatment. People were dying, and the drug AZT was helping people. So they stopped that trial early. Okay. Any questions? All right. So now we talk about the kind of things that we do at Google, which kind of go by the name of multi-arm bandits. Yeah, do you know what a one-arm bandit is? Who knows? One-arm bandit's a slot machine. You put your money in, you pull the arm, and it takes your money. A multi-arm bandit is where you have multiple alternatives. Maybe it's multiple slot machines or multiple arms in a clinical trial. You don't know which one is best. And so what you do is you have a trade-off between trying the different arms to collect information on which one is best versus just playing the one that you think is best at this point, that's giving you the best results so far. So on the web pages, this means that I'm deciding between sending traffic to these multiple arms or just sending traffic to the one that's been best so far. And A pretty effective way to do this uses a Bayesian approach, where we basically estimate for each arm what's the probability that this arm is best at this point. And say there's one arm that's looking pretty good. There's a 70% probability it's best. We're going to send 70% of the traffic there. But we're still going to send that other 30% to some of the other arms because, you know, they could be best. And by doing so, we'll learn a bit about them. Over on the right is an example of true probability. So the arm number 1, the red arm, is best. It's got the highest success rate. But arms 6 and 8 are pretty close. And then there's some really crappy arms. So with this Bayesian approach, what happens is the crappy arms pretty quickly stop getting any significant traffic. And the middle to good arms keep getting traffic for a while, and then eventually over time, the top 3 arms are getting almost all the traffic, and then eventually the top arm gets all of it. Any questions? All right. And with the Bayesian approach, we do this with simulation. On the left is an example where we have done 50 trials of arm 1 so far. We've gotten quite a lot of information there, but only 3 trials of arm 2. And so there's a lot of variability up and down. We really don't know much about the probability of success for arm 2. And the proportion of dots that fall above the 45-degree line is our estimate of the probability arm 1 is best. That arm 2 is best, rather. And so then when we collect more information from arm 2, that uncertainty narrows down, and we end up pretty certain that arm 1 is best. So some observational data. Little quote from the father of modern advertising. This is a project I worked on for our display ads effective. So we know how Google makes money. How does the rest of the web make money? You've got a page with some content, something that interests people. And for most websites, the way that they would make their money is by showing ads, like these display ads. Over on the bottom right here, HTC advertising a phone. Now, how do you measure the effectiveness of those ads? Is that money wasted? If somebody clicks on the ad, we know. That's a good sign. How many of you click on those ads? Yeah. Now, very few people click on those ads. That's really not what we're interested in. That's not why they show these display ads with the hope of clicks. They show the display ads with the hope that this will make people aware of the brand, give them warm, fuzzy feelings about the brand, and that they will then go and search for that brand or go and buy. Okay, so there's the ad. Okay, did that have an effect? And different ways that you can estimate the effectiveness of an ad. You can do focus groups. That's expensive. You can do controlled experiments, or you can use observational data. So we know how many people click on ads, but that's pretty rare. And then the questions we're interested in are, do people know about the brand? Are they interested in the brand? Are they more likely to go navigate and search? So these 2 things are things that we can measure at Google in some cases. In some cases, we have data where people have opted in to let us track that. Okay. Make people more likely to buy. We don't have that data. So in this case, what we're going to do is compare people who saw the ad to people that didn't and track their behavior over time for the people that opted in so that we see who did seeing the ad make you more likely to navigate to the HTC site, or did it make you more likely to search for HTC? And naive way to do this would be to just compare. Okay? You saw an ad for HTC. You did not. Okay? And then, okay, so these people saw the ad, these people didn't, and then just compare the proportion in this group to the proportion in this group. That's not so good. These people saw the ad, and incidentally, detail on this, these people saw the ad. These people came to the sites, the websites where the ad were shown, but they didn't see the ad. Okay. Now, why? Well, a big reason was that these people spent a lot more time on that site. They gave themselves more chance to see the ad. These people spend a lot more time on the web than these people do in general. These people do a lot more searches, they do a lot more navigations. And if we then just compare how many searches did these guys do for HTC compared to these guys, it's a biased comparison. So we have to correct for that. This is an example. The people who, in the 7 days before seeing the ad, these people did 5 times as many navigations. 91% of these guys searched on Google, only 61% of these people. Okay, so the naive comparison would be biased, and we correct for that. Way we do that is using a logistic regression. I'm not going to go into great details, but basically, over on the bottom, the x-axis is a combination of things that, in the absence of the ad, would predict how likely you were to search. Like the more time you spend on the web, the more searches you do in general, makes you more likely. And so we end up with a curve for the exposed and a curve for the controls. And the difference between those two curves is our estimate of the effect. Any questions? All right. And at Google, we don't do one study. We do things at scale. We were doing thousands of these studies. So initially, we would play with one data set at a time. But then once we get things going, we're running thousands of these studies, hundreds every month, on automated fashion. Okay. Now, that was an earlier version where we're working with observational data. And now the current version actually uses experiments where we randomize whether you are in the experimental group or the control group that doesn't see the ads. And we're using surveys. Now, let me tell you a little about surveys at Google. Newspaper advertising is going down. Newspapers in this country are not doing well. How many of you read newspapers? Okay. Fair number, but not nearly as many as it would have been 10 years ago. Okay? And the advertising has gone down even more. It used to be that the way people did advertising locally was in the newspapers, and now they do it elsewhere. And well, Google benefits from that. A couple guys at Google were talking about what Google could do to help newspapers. One of the guys' wife was a journalist. And they came up with this idea that, okay, so what's the problem with the newspaper website? How, with them making money? They've got this great content. You want to read a story. You go to their site. They ask you to pay. And what do? You go away. You look for the content somewhere else, right? So they came up with this idea of showing a survey. You answer a 1 or 2 question survey. And then the person that's sponsoring the survey would pay. Google acts as an intermediary. Google pays the newspaper site. The newspaper makes some money. They developed this in their 20% time. So one of the great things about Google is this idea. It's a place that gives people a lot of autonomy, a lot of ability to run with new ideas. 20% time says you can take 20% of your time to try something. Okay? It should be something that has the potential to be of value. And so they started, in their 20% time, developing this survey process to benefit newspapers. So you go to, say, the Christian Science Monitor site. You want to see the story. You answer a survey to be able to see the story. You create the survey online. You could do this right now. You've got wireless. You could go to Google Consumer Surveys. You could set up a survey, take you about 5 minutes, and be collecting results immediately. And it's pretty cheap. It's about 10 cents a response for broad targeting. If you're targeting narrowly, it's a little bit more. Okay. And so then the newspaper gets paid. And you get results like this. There's some breakdown by demographics to the extent that we know demographics, and you get the answers. So it's cheap. You get the results quickly. You can try different versions of your survey and see what works best. And it ends up being pretty accurate. Now, surveys in this country, the way they used to be done was random digit dialing. Okay, people had landlines. Anybody remember landlines? So you get a phone call, somebody asking, would you answer a short survey? Okay. Well, with cell phones, they're not allowed to do that, and with landlines, people won't answer the surveys anymore anyway. Okay, so there's a big gap in how do you collect information, and this kind of fills that gap. And the response rates are pretty good, and Nate Silver in the last presidential, yeah?
How do you control for potential bias in the answers?
Control for potential bias. So a couple of ways. One is that we started with just newspaper sites, and that's sort of a biased audience. It's now broadened out. Another is to the extent that we have information, demographics or whatever, we can control for, we can do some post hoc adjustment for those. Okay. So for asking a question, you get some Google sunglasses. Pass that down, please. And there was one back there. We're targeting you. So Nate Silver found that that these particular surveys were the most accurate source of data that he had in predicting the last presidential election. So just to wrap up, we've got a lot of statisticians at Google, and we've got a lot of people that do statistics. Google lives on data. Google learned very on to appreciate statistics. They treat us very well. They appreciate what we do. We've got about 1,000 people on our statistics email list, statistics discussion list. Got about 1,000 people on our users list. They're not all statisticians, but there's a lot of people doing statistics. So here are some of the different teams with statisticians at Google and some of the different projects, some of the different locations. Okay. We're always looking for good talent. And lots of other places are looking for talent too, both private and government. A lot of challenges, and there's a lot of jobs. Okay. That's it. Thank you.